Alright, so this time we're taking a look at section 16.1, which deals with vector fields. Alright, so let's take a look at the definition. We're going to have D. It's going to be a set in R2. And then a vector field on R2 is a function f. That's going to assign to each point in D some sort of vector that we're going to call big F of x, y. This is a two-dimensional vector. Alright, so this f can be written in terms of its component functions. That we're going to call P and Q. And so you might write it this way. So we have f of xy is equal to P of xy times I plus Q of xy times j. Or you might write it in component form. Use this notation. Or you might even write it as f equals pi plus qj. Now let's keep in mind that P and Q are actually our component functions, but they're scalar functions of two variables. All right, so we can do the same sort of thing in 3 dimensions. We have a definition for vector field on R3 as well. So once again, we're going to let E be a subset of R3. Then a vector field on R3 is a function we're going to call f again. But this f is going to assign to each point x, y, z, and E a 3-dimensional vector. That we're going to call big F of x, y, z. And similar to what we see over here, we can write the f of x, y, z as follows. just this time we'll have 3 components. So we'll have p of xyz I plus q of xyz j plus r of xyz k. All right. Now, these vector fields can model all sorts of different things. One example that you might see is you can model things like wind speed and direction. Ocean currents is another. But basically, what's happening, if you want a sort of geometric representation, is in the two-dimensional case, you would have maybe a situation like this. And you have some sort of function f defined on some set D in R2. And if you were to take a look at a particular xy that's in D, then plug that xy into the function f and they'll give you a vector. And when we start to draw our vector field, then what we'll do is we'll take a representative set of points, and we'll take those points, we'll plug it into f, and for each one of those points we'll have a vector f of xy. And so in a case like this, maybe your f of xy looks something like that. Right. So maybe that's what you get. But at a different xy, your vector could look certainly completely different. So if you were maybe at this location, who knows, the vector might look something like that. Or if you're at this location, maybe the vector looks something like this. All sorts of different possibilities are out there. And in 3 dimensions, you carry forward with sort of the same idea. It's just, we're carrying this forward into a 3-dimensional setting. And so you might have some sort of point here, maybe that's an xyz. And who knows, you might have a vector that goes like this. And of course, going like this is a little bit of a mystery when you think about not having really too much perspective here. But the idea is that what would happen is you would plug in your point xyz, and that will get plugged into the function f, and that would give you some sort of vector f of xyz, which you would draw so that the initial point was at xyz. Get a whole bunch of different points perhaps, and you can get a pretty good idea of what your vector field looks like. Now, let's take a look at a specific example. And so for this example, we have a vector field on R2. It's going to be defined by f of xy is negative yi plus xj. So we're going to describe f by sketching some of the vectors f of xy. All right. And so we'll take some points, some representative points, and we're going to figure out what the different vectors are going to look like here. And so I think what I'm going to do is start with maybe a collection of 4 points and then work from there. And the collection of 4 points that I'm going to use, I'll have one point at 1, 0, another one at 0, 1, another one at -1, 0, another one at 0, -1. And so for each one of these points, I'm going to plug into the given function and see what vector I get. All right, so if you take a look at f of 1, 0. All right, well, in that case, we would have x is 1 and y is 0. So you have a -0i plus 1j. That's just j. So what I would do is I would go over to my graph here, and I would draw a vector whose initial point is at 1, 0, and that vector will be j. So my vector would look like that. Now let's take a look at other points. So maybe we're at the point 0, 1. So x is 0, y is 1. We have a -1i plus 0j less a -i. So we would draw the vector so that the initial point is at 0, 1, and we would draw the vector -i. So that's what it would look like. And then we'll take a look at f of -1, 0. Well, if x is -1 and y is 0, you get a -0i plus -1j, that's -j. Draw the vector so the initial point is at -1, 0, and -j is your vector. And then if we take a look at f of 0, -1, then we have x is 0, we have y is -1. So you have -1i is I plus 0j. Okay, so this vector is I. Draw the vector so that initial point is at 0, -1, and then draw I. So the first 4 vectors we have look like this, but we could certainly take other locations and figure out, well, what do those vectors look like as well. And so if we were to go to, let's say, maybe a 3, 0, or maybe 0, 3, maybe just change each one of these 1s to 3s and -1s to -3s. Okay, that gives us another collection of 4 vectors. And f of 3, 0, you got x is 3, you got y is 0, so -0i plus 3j, that's 3j. So draw the vector so the initial point is at 3, 0. Then we can take a look at f of 0, 3. X is 0, y is 3. Get a -3i plus 0j, that's a -3i. So initial point is at 0, 3. And -3i is your vector. Looks something like that. Then we'll have f of -3, 0. X is -3, y is 0. -0i plus -3j, that's a -3j. So initial point is at -3, 0. The vector is -3j. And then we'll have f of 0, -3. And for that, we'll have x is 0, y is -3. Minus -3i is 3i, plus 0j. Okay, well, you got 3i. So 0, -3 is your initial point. Draw the vector 3i. Okay, so that's what we have so far. I do have just a few more vectors I want to put up there. So let's take a look at some locations that are not on one of the coordinate axes. So maybe we'll take a look at f of 2, 2. So you have x is 2, and you'll have y is 2. So you get a negative 2i plus 2j. Negative 2i plus 2j. All right. So what we have to do here is put our initial point at 2, 2. And then the vector is negative 2i plus 2j. So we need to move to the left 2 and up 2 to plot the terminal point. Right, so that'll be our vector. And then we'll take a look at f of negative 2, 2. Here you have x is negative 2 and y is 2. So negative 2i plus negative 2j, negative 2i minus 2j. So negative 2, 2 is our initial point. From there, we will move left 2 units and down 2 units to plot the terminal point. So you get a vector that looks like that. And just a couple more. We'll take a look at f of, how about we go with negative 2, negative 2. So x and y are both negative 2. So minus a negative 2, or 2i, plus negative 2j, 2i minus 2j. Our initial point will be at negative 2, negative 2. And then the vector we draw, 2i minus 2j, we'll need to move to the right 2 units and down 2 units, plot the terminal point. And then finally, f of 2, negative 2. So we'll have x is 2 and y is negative 2. So minus negative 2 or plus 2i, and then plus 2j, so 2i plus 2j. So 2, negative 2 will draw our initial point. And then drawing 2i plus 2j, we're going to move up 2 and to the right 2 to get to the terminal point. And so this is a collection of vectors that helps us get an idea of what this vector field looks like. Now, this sort of stuff can be done in 3D as well, and it's, for probably most people, it's probably best to use technology to try to get those worked out. So, moving right along. So here we're going to suppose that little f is a scalar function of 2 variables. Now, remember, from a while back, we took a look at this idea of a gradient. So the gradient function you might recall, is defined by the following. And so to get the gradient of f, we'll have partial f with respect to x as I, partial f with respect to y is j. Now, if you think about it though, this has the form of some sort of p of xy times I plus q of xy times j, which means that this really is just a vector field on R2. So once again, this is a vector field in R2, and what we refer to it as the as a gradient vector field. All right, so let's take a look at an example. So here we're going to find the gradient vector field of f of xy equals x squared y minus y cubed. All right. So to find the gradient vector field, this is what we do. Take a look at the partial of f with respect to x. And if we do that, then we have to keep in mind that y is treated as a constant. So y treated as a constant, partial f with respect to x, you're going to get 2xy minus 0 or 2xy. So 2xy will be our I component. And then we have to take the partial of f with respect to y, and it's partial f with respect to y, then x is treated as a constant. And so we'll have an x squared minus 3y squared. So that's our gradient vector field. 2xy I plus x squared minus 3y squared j. Now, I'm not going to draw this, but if we were to take a look at drawing this vector field together with contour map, and draw it together with its level curves, and then what we would find is that the gradient vectors are perpendicular to the level curves. And these gradient vectors are going to be longer if the level curves are closer together, and shorter if the level curves are further apart. Just keep in mind that the value of your directional derivative of f in the direction of unit vector u is the length of the gradient vector. And so if the level curves are closely spaced, then that indicates a steeper graph. So that's why your gradient vectors will be longer if the level curves are closer together. Now, moving on to our last definition. Take a look at what it means for a vector field to be conservative. So the vector field is conservative if it is the gradient, and let's call this vector field f. Okay, so vector field big F. We'll say it's conservative. Alright, so once again, vector field big F is conservative if it is the gradient of some scalar function. Alright, so if you think about what that really means, it means that there exists a function little f such that big F is the gradient of little f. Now, this function, little f, is called a potential function for big F. And in some of the following sections, we're going to be looking at different ways that we can determine whether or not a given vector field is conservative. But in the meantime, we have some recommended exercises. And these recommended exercises are 1, 3, 9, 11 through 14, and 25.